Welcome. In this video, we'll be looking at the speed limits of Mosfet transistors, and in particular how their speed is related to the capacitances that they have. And we'll see that results in the unity gain frequency, where the gain of the transistor becomes less than 1 above that frequency. Let's get started. So we'll be looking at the capacitors within Mosfet transistors. So we'll be looking at Mosfet transistors. And we'll also be looking at the unity gain frequency, which is defined as F sub capital T. So we're using a capital T here to represent the unity gain frequency for a transistor, as opposed to for a circuit. So we'll see that Mosfet transistors have parasitic capacitances. They're always present. And they effectively limit the speed of the transistor, and that hence they also limit the circuit speed. So they limit our transistor speed, how fast it will go, and as well that limits our circuit speed and what we can do with them. We'll see that the parasitic capacitances that we have are 4 parasitic capacitances. We'll see there's a gate to source parasitic capacitance, a gate to drain parasitic capacitance, and these two capacitances are inherent to the operation of the transistor. So we need these capacitances in order to make the transistor work as intended. The other two capacitors will be the drain to bulk capacitance and the source to bulk capacitance. And these depend upon the area of the drain to source regions. And these regions are needed in order to connect to the drain to source. So they're not inherent to the transistor, but if we want to connect to the transistor, then we need to have drain to source regions, and therefore these capacitances will occur. But they don't help with the operation of the transistor, they just help to make it be able to connect to the transistor themselves. We also will be defining the unity gain frequency for a transistor, F sub capital T. What we'll find is if we're operating at a frequency higher than F sub T, then the gain of this transistor becomes less than 1. In other words, it's no longer giving us gain, and it's operating more like a passive element, and so you have to question the use of the transistor at all when you're working above that frequency. In fact, it doesn't give you any benefit. What you'll find though is that we'll find this unity gain frequency for the transistor itself, but in terms of circuits, they generally cannot operate all the way up to F sub T, and that they're actually closer to perhaps F sub T divided by 10. So in other words, if we have a transistor that has, say, a 300 gigahertz unity gain frequency, this is really just the transistor all by itself and not connected to anything. Once we start connecting it to other transistors and we have wiring and we have everything else that comes into play, generally it can go up to maybe 30 gigahertz for a 300 gigahertz operating transistor, or less. It depends on what you're trying to really build here. So let's look at these different capacitances. So start, and this is our model for our transistor. We'll see that we've added now these 4 capacitances: CGS, CGD, CSB, and CDB. So the gate to source down here, the gate to drain here, source to bulk here, and the drain to bulk here. So let's start off in looking at the gate to source capacitance. So the gate to source capacitance is because we have the gate up here, and it's going to have a capacitance between that and the channel, which is underneath the gate. And remember, there's a pinch-off region that occurs somewhere here, where there's the drain is on the right-hand side and the source would be on the left-hand side. So this whole capacitance between these two red lines here, this capacitance, which would be the gate to source capacitance, it would include this region around here and here. So that's our gate to source capacitance. We will also then have the gate to drain capacitance. Gate to drain capacitance, shown here, is going to be the overlap region right here relative to the drain at the bottom side here. And what we see is that the overlap distance, which is given by this spacing right here, determines what the gate to drain capacitance is going to be. That overlap must occur in order for the transistor to operate as a transistor. Remember, we're trying to get current flow from the drain to the source. If we don't have an overlap, it's possible that we won't have be able to create a channel between the drain and the source, in which case our transistor would not operate correctly. So we need to always have an overlap at the source and at the drain to ensure that the gate is creating a channel underneath between the drain and the source. Now, also I just want to recall or point out that all of this is for the active region. We're looking at the active region at this point. In our body, when I say the bulk, I mean the body or the substrate. In this case it would be P-, since it's an NMOS transistor. Now for the drain to bulk capacitance, shown here, that is due to the this region is the drain, so this whole area is the drain, but the capacitance is due to this reverse bias diode that occurs all along here. So this edge right there really looks like a reverse bias diode, where this is the P- and this is the N+. So it looks like a diode at this point. It's reverse bias because our drain will be at a higher voltage than our P-, or equal in voltage. Even if it's 0 volts, we consider that reverse bias still. It's not, when it's not forward biased, we consider it reverse biased. And so the total area that we see there will be our drain to bulk. Now, in the case that when we're building this, the distance that we go down here is not something we can control, but that is part of the capacitance that we have to worry about. But how deep it goes, if it went much deeper, would cause more capacitance. But that's set by the foundry or whoever is the technology itself. But what we do have control is how far we build this out. So we could build it out to here instead and have this whole region being our drain. But of course then we would have more area at the bottom here, this edge right here, and therefore more capacitance. So typically we build this as small as we can if we want to minimize that capacitance. So in this case we want to just build it in this region over here. Of course we have to go past the overlap region because we have to be able to connect with a wire down from the top over here. Now the source to bulk is the very same thing but on the other side. So again it would be this whole region here, and that would be the reverse bias voltage of that junction. In the case where the bulk is equal to the source, which occurs in many cases in analog circuits, so in that case we'd have these two voltages, the bulk and the source being the same, in which case the voltage across this would always be 0, and then the source to bulk capacitance really would be unimportant in that case. So we would not have to worry about the CSB when the voltage of the base equals the voltage of the source. So let's look at the equations for these capacitances. So first off, we have for the gate to source capacitance, it's equal to the area, which will be under the width times the length. And because the pinch-off region is very small, we'll assume that the length goes right across. So it's going to be the width times the length times Cox. So it'll be this part right here. So Cox is the gate capacitance per unit area. So width times length times Cox will be that region right here. But there's also a 2/3 factor because our channel is actually triangular shaped. So due to a triangular shape where the more charges are inverted over, or the channel is more inverted on the left-hand side and less inverted over on the right-hand side, we get this triangular shape, and that results in this 2/3 parameter here. But now adding to that, we also need to add this part here. This part accounts for the overlap at the source region here. So if we're looking right here, it's this small overlap part. And we have that that will be the width times the overlap length times Cox in this case. The next capacitance we have is the gate to drain capacitance. Well, that's going to be very similar to this one here. It's the overlap capacitance now at the drain side, so it's a width times the length of the overlap times Cox, which will be this region up here. So we're looking right up here. Now for the drain to bulk, we have that the drain to bulk is a function of the reverse bias voltage that we have across it. So it will be whatever the capacitance is for that region, and that will include the area of it, but it will be scaled by the bottom, by the term below, which accounts for the reverse bias voltage potentially not being zero. So the numerator, in this case, C sub D0, is the capacitance from the drain to the bulk when the reverse bias voltage is equal to 0. And in that case, VDB would equal 0, so this bottom term would go to 1. But if it's not 0, then VDB gets divided by this term here, which is V naught, where V naught is given by the junction built-in voltage of that diode, which is typically around 0.7 volts. Then we have the similar equation for the source to bulk, except we're using the C source to bulk with 0 and this voltage for the source to bulk as well. If we have that the drain and source areas happen to be the same, then of course we'll have that the nominal drain to bulk capacitance is equal to the nominal source to bulk capacitance, but of course the source to bulk voltage may be different than the drain to bulk voltages, so you would have to still account for that with the bottom part of these two equations. And this goes through what I just mentioned. Now in the triad region, things change a little bit. The big difference being that we no longer have that 2/3 term here. So in the gate to source for the active region, we had a 2/3 term right here, and that is now gone and just becomes 1. And the reason for that is that the channel is not triangular shaped in the triad region, it's just straight across the transistor. And so you can ignore that term, and so we have the adjustment here. The other capacitance values are all similar to what they were in the active region. So now if we look at the small signal model, going back to the active region, we look at the small signal model, then we have these added capacitances here. So these 3 added capacitances, and we'll assume that VSB is equal to 0, so we don't have to account for this 4th capacitance between the source and the bulk. And so we've also connected the drain to bulk capacitance to the source, because we're assuming the source and the bulk are tied together. So we have this model for a transistor. Without those 3 capacitors, it would just be our standard small signal model for a Mosfet transistor. Now we would like to have a figure of merit for our transistors to know how quick they are, how fast they are from one technology to another, or if you're in design, how you change the widths and the lengths or the overdrive voltages. so how much current you put through them as well. So we'd like a figure of merit to determine our transistor speeds. So we look at the unity gain frequency as that. So the part where the gain of the transistor goes to a gain of 1. And we'll define this to be omega sub capital T. So we're using a capital T here. And that will be equal to 2 pi f sub capital T down here. Those are because these are the unity gain frequencies for the transistor, not for the circuit itself. And omega T is in radians per second, and ft then will be in hertz. So we can either write our figures merit in radians per second, but it's commonly written in hertz. The definition for omega T then is where our short circuit current gain is equal to 1. You may ask why we're looking at current gain instead of voltage gain, and we'll talk about that a little bit later on. So what we'd like to do is we'd like to take a circuit like this, shown here, and we'll apply a current input, which is now a function of frequency. So this is I sub I, which is a function of S. We'll look at the output, which is also a function of frequency. And we'll look at the ratio from I out to I sub I, the input current, as a function of omega T. So as a function of omega. But when it's omega is equal to omega T, we'll define that to be the case where the gain has reached 1. So when the gain, the small signal gain of the current gain, it will be dropping and going lower and lower as we go higher and higher frequencies. When it finally reaches a gain of 1, we'll call that frequency omega T, capital T. And of course, the bias has not been shown for this circuit. There'd be have to bias this properly, but this is just a small signal model for that we're looking at, so we'll assume the bias currents are all done and they're all ideal. So a small signal model for this circuit that we had above is shown here, where we have our input current. But we'd like to recall, this is looking at the output is short circuited, so we're looking at the output short circuit current, because we've grounded this node here. So we have over here in our model I sub out, and that's also short circuited to ground. So our goal is to find the gain from I sub I to I out as a function of frequency. If you notice, by shorting the output, C sub D, the drain to bulk capacitance, is unimportant, and the output resistance is unimportant, since the current across both these will be 0, since the voltage across both those is 0. So those won't come into play, and so we'll be able to better determine what the intrinsic high frequency current gain is for this transistor. So what we have is we can look at the gate to source voltage. So we need to write down a couple of equations in order to solve what I out over I sub I is. So we have the V sub GS will be equal to the input current times Zin. So we have that VGS is equal to I sub I times Zin. Well, Zin is just the capacitance looking here, which is CGS, and the capacitance looking in this direction, which is CGD, since the other side of the capacitance here is connected to ground through this path here. So we have the Zin is just a parallel combination of CGS and CGD. So we can write that VGS is I sub I times the impedance times the parallel impedance of CGS and CGD, which is just 1 over S CGS plus CGD. So that's equation 1. Next, we can just write this current here, I sub 1, so the current through the gate to drain capacitance is just equal to the voltage across it, which will be VGS, again because the right hand side is connected to ground, and the left-hand side is VGS. And it will, so I sub 1 will be VGS divided by the impedance of that capacitance. So we'll have that I sub 1 is VGS divided by the impedance of that capacitance, which is just 1 over S times C GD. So we can rewrite that as I sub 1 is equal to S times CGD times VGS. That still doesn't give us the output current. We need the output current here. And finally, we can write that the output current, this output current here, is equal to this current minus this current because of the direction that we have in the arrows. So we have that I out is GM VGS, which is this current, minus I1. We already have I1 from here, so we can then write the next equation. So we have I out is given by this. We can factor out VGS, and we have our second equation here. So we have two equations, 1 and 2. We can now take the VGS and substitute that into here in order to get I out divided by I sub I. So if we go through that, we end up with this equation here. Now, what we like to do is we want to find, this is going to be a function of frequency, and so what we need to do, what we need to find is when the frequency, when this function goes to 1, that frequency is equal to omega sub t. So in other words, by definition, I sub out over I sub I at j omega capital T should be equal to 1. So we can just take the one above, and we have then this equation here. So this is one equation, and we only have one unknown in this equation, and it shows up here, and it shows up here. So we'd like to solve this for omega sub capital T. And that will be where our current gain goes to 1. We can split this up and write this as GM divided by this, so this would be this part of the equation, and then subtract this part over here, which would be this part of the equation. So just break up into two parts. What we see is this part here is CGD divided by CGS plus CGD. If you recall, we said the gate to drain capacitance was the overlap part of the transistor. So generally, C gate to drain is much, much less than CGS by perhaps a factor of 5 or a factor of 10. So it's quite a bit smaller, could be even much smaller than that. So we can typically then ignore this whole term here. We can ignore the term CGD divided by CGS plus CGD. Why is that? Well, we're looking at when this is equal to 1. If this value here is equal to 0.1, then we can pretty much ignore it and just worry about this term over here. We'll have 10% error, but we'll be still a fairly good figure of merit. If CGD over CGS plus CGD is 0.01, there will only be 1% in error. So we ignore the second term here, and we have our equation then given by this. We solve this for omega t, and we end up with the final result that the unity gain frequency for a transistor is just given by GM divided by CGS plus CGD. That's in radians per second. If we want it in hertz, it's equal to GM divided by 2 pi times CGS plus CGD. Now we can draw the graph this. So if we look at the, going back to what we had, is we have this formula up here. But if you recall, what we did is we ignored, we basically said this term here goes to 0. So we ignored this part over here. So we'll just plot it without that term. and we have this green equation right shown. And we can plot that versus frequency. So we can plot this, and what we see is that it looks something like this. So a curve that comes down like that. So what this is, it looks like an integrator. The reason it looks like an integrator is we have a term, some constant divided by S. So this is an integrator dropping off at minus 20 dB per decade. So as we double in frequency, we have in the gain. We'll go 10 times up in frequency, we drop by 10 the gain. And when the gain finally reaches 0 dB, we define that to be omega sub capital T. So we have this equation here, that omega sub capital T is equal to GM over CGS plus CGD. And we'd like to look at how does the FT change as our technology changes or our circuit choices change. As a designer, we have control over the overdrive voltage, the width, the length. So let's see how things would change here. So what we have is that GM, if you recall, is given by mu n Cox, width over length times V overdrive in the active region. And we're only looking at this unity gain frequency in the active region. And we have that CGS is given by 2/3 width times length times Cox. If we assume that the gate to drain voltage, C gate to drain, so the gate to drain capacitance is much less than the gate to source capacitance, then we can rewrite this one up here and just ignore the CGD. So we assume that CGS is much greater than CGD, so we'll ignore the CGD part. So if we do that, we can rewrite that equation shown as here. Substitute in GM, which will then be here. Substitute in CGS, which will be here. And we can now start canceling some things. We see that the W's can't cancel. The V, not the V overdrive. V overdrive stays. But the Cox cancels as well. And so if we rewrite that, we find that FT is 3 times mu n V overdrive divided by 4 pi L squared. So the width no longer comes into play. And you find this is typical in analog circuits, that if you maintain the same overdrive voltage, then increase in the W does not make things faster or slower. It generally just burns more power, but it does not change the speed of the overall circuit. The other thing, you actually find this in digital circuits as well, that if you have some digital circuits that operate with a width equal to, let's say, 1 micron, and then you double all the widths all throughout the circuit to be 2 microns, the circuit doesn't run any faster, assuming there's no parasitic capacitances, so no wiring capacitances that we're taking into account. We were just driving other transistors, and all the other transistors are all scaled equally. So what would happen is you burn more power, but you wouldn't go any faster. So generally people try to use minimum sized transistors in digital circuits because there's no benefit to increasing the width unless you're driving parasitic capacitances or wiring capacitances or a large number of other transistors. But so what we have then, shown by this equation, is that FT is now independent of W, but it's proportional to 1 over L squared. So choosing a length that's not minimum, you're going to be going slower. So if you just worry about speed, you want to be choosing the minimum length you can, or you want to go to a technology which has a shorter length. By going to a shorter length, you get a speed increase, in fact by square increase. So if you can reduce the L by 1/2, you'll get a 4 times increase in speed. It's also proportional to V overdrive. So if you make your V overdrive small, you tend to go slower. If you make your V overdrives larger, you tend to go faster. And finally, and these are under your control as a designer. The last one is not typically under your control. We find that it's proportional to mobility, mu n. And so that's technology dependent. And so if you want it to go faster, you'd want to increase the mobility of the transistor. And what you'll find in a lot of technologies, they actually add some germanium in order to speed up the mobility of the transistors, because pure silicon does not have as high mobility as germanium. So the next question we have is, why are we using a current gain? Why don't we use a voltage gain in order to find our unity gain frequency? Well, let's look at that for a second. So let's imagine somebody came along and said, we're just going to do the similar thing, but we'll use an ideal current source, and we'll have a voltage source which is ideal driving a transistor here. So what we find is that this voltage source V sub I has to be driving C gate to source and some more, the C gate to drain, which is tied to the output voltage. So we have the impedance that V sub I has to drive is the gate to source capacitance in parallel with the gate to drain tied to V out. Now let's just ignore this part here. Just worry about the CGS for now. So what we have, so just considering the CGS, we have that Zin is equal to 1 over S CGS. And the input current is equal to VI divided by the impedance. So I is equal to V over R, and Zin is our equivalently R, or impedance in this case. So Z is 1 over S CGS. So what we find is that I, the current, is S CGS times VI. In other words, I will go to infinity as omega goes to infinity. Because as we let S equal j omega, then this term as omega gets larger, this will also increase. So our current into this system becomes extremely high as the frequency goes high. So that's a problem. We can't actually build this circuit, and it's not really realistic because what we're measuring then is the ability of building a source that can drive a very, very large capacitance at a very high frequency with delivering a lot of current. So something has to do that, and the previous stage would have to do that. So generally that's not a good way to look for to try to figure out what the speed of a circuit would be. How does a current source differ? When the current source case, we're driving again CGS, and we're developing, in this case, a voltage. So in the first case, we were driving it with a voltage, and we needed a certain current to drive it. In this case, we're driving it with a current, and it generates a certain voltage VI. What we find is that as omega goes to infinity, in this case, VI actually goes to 0. So it's not going to infinity, it's actually going to 0. So this is a much more realistic situation, and you can build it with some lab benches or lab equipment, and as long as you can build I sub I fast enough, you're not having to deliver a lot of power into it. So that's one aspect of it. So let's assume that we can somehow build a VI with a large power delivered to the input, which would be extremely difficult in the lab anyway. Let's imagine we could do that. And so then we want to build a circuit that looks something like this. So we're going to build this type of circuit here, where now we're going to make the two current sources ideal. We'll make M1 and M2 identical. Because we don't want to drive nothing, that's not realistic. We want to have a transistor driving another transistor, which is the same size, it may drive another transistor the same size, and so on. So we'd like to know, in the digital world, what we would typically do is a ring oscillator. So we'd build minimum size inverters, put them in a ring, and see how quickly they'll oscillate. And that would give us an idea of technology. So in the analog world, we'll just drive transistors all of the same size. Sorry. So in this case here, we'd like to know, well, what is the gain from VI to this node here in the middle at this point? So V out over VI will still have some finite bandwidth. Will drop off. And we'd like to know, when is the gain from VI to VO1 going to be equal to 1? In this case, we're going to use our analysis, and we're going to ignore something called the Miller effect. It turns out that there's actually the capacitance over here, which is CGD, and having a gain between VO1 and VO2 actually changes the size of CGD, the effective size of CGD. But we're going to ignore that effect and just assume that Vout is not making that difference, and we'll just consider it a ground at this point, just to approximate it at this here, because we don't really haven't studied the Miller effect yet. We'll look at that in another video. So to figure out the gain from here to here will look like a low-pass filter. In order to figure out what that low-pass filter looks like, we need to know the DC gain, and we know the 3 dB pole frequency. Well, we know how to find the pole frequency. The pole frequency is we just find the capacitance at this node, so we'll call that C sub P, the total capacitance seen at that node, in parallel with the resistance seen at that node. So we see that the capacitance here, C sub P, the parasitic capacitance, is given by the gate to source voltage of 2, so this gate to source voltage, plus the gate to drain voltage of 2, so this gate to drain voltage here, plus the gate to drain voltage of 1, so the gate to drain voltage of 1, which would be here, plus the drain to bulk of 1, so plus this drain to bulk of 1. So all of those capacitances are tied on to this CP1 at this node. The resistance seen at this node is just RO1. So the resistance seen at this node is just the impedance looking down RO1. So we have that the pole frequency is just given by 1 over RO1 times CP. The DC gain we already know, that's just the gain from here to here, and that's just a single transistor gain stage. So it's just GM RO1. So the DC gain, given by this, is just GM1 RO1. So now we can write that the gain from the input voltage, if it was an ideal voltage source, to the output VO1, would just be the DC gain M1 times RO1 divided by 1 plus S over omega P, where omega P is our 3 dB frequency. So our omega P would be showing up right here as omega P. Now, but we're really interested not at omega P, but we're interested in this frequency here. We'd like to know, when does a gain of this transistor become less than 1? So that's our unity gain frequency for this circuit from here to here. And what we know from before is that we can estimate the unity gain frequency of a first order low pass filter if the DC gain is large. So if GM1 RO1 is much greater than 1, then we can estimate this as just multiplying the two together. So if we multiply omega P, if we multiply omega P times GM1 RO1, that would be a good estimate for omega T when GM RO is much greater than 1, or when the DC gain is much greater than 1. So in this case here, we have this, and that works out then just to be the RO1s cancel out, and so we see it's GM1 over CP. So we end up with, finally, that the unity gain frequency for this circuit, not for a single transistor, but for this circuit, is given by GM1 divided by all this. And what we see here is this looks very similar to what we saw before. We have a GM1, we have a CGS, and we have another CGD, but we have these other two terms. Now first off, we note that this is the GM1, where this is related to transistor 2. We've assumed that M1 and M2 are identical, so this would be exactly the same as omega t right here. These extra two terms are because of the circuit that we see, because we have an extra transistor in here and we have a drain to bulk that we're also accounting for. But we do see that there's a fairly close relationship between this equation and this equation, which is the equation for a single current gain for a transistor. So they're very, very similar, and we see that omega capital T, the unity gain frequency for a single transistor for the current gain, is very similar for this particular circuit for the voltage gain of this, for the input stage to the output of the first stage. So we see that omega t is a pretty reasonable estimate to estimate omega t in this particular circuit. In fact, if omega t, capital T, was doubled, roughly omega small t would probably likely be doubled as well. Remember, we would double it for both transistors since both transistors are identical. So we see that this is the reason that we tend to use the current gain for in order to measure the unity gain frequency for a Mosfet transistor, as well as for bipolar transistors. We use current gains as well. That's it for this video, and thanks for watching.